So, in this video, we're going to talk about AP Chemistry's topic 4.9, oxidation-reduction reactions, also known as redox reactions. The two things we want to focus on is how to identify whether a substance is being oxidized or reduced. And then the second thing we want to talk about is how do you balance redox reactions. So first, let's just be able to identify whether an element is being oxidized or whether an element is being reduced. And in order to do that, you need to know one thing: oil rig. So oil rig, why oil rig? So oil, oxidation is loss of electrons. So when we're talking about redox reactions, we're always talking about electrons being lost by an element or electrons being gained by an element. And in order for a redox reaction to occur, you must have both occur. So oxidation is the loss of electrons. So if an element loses an electron, that is an oxidation reaction. But you can't just have oxidation. Where does that electron go? Well, the electron has to go somewhere, and so that's where rig comes into play, oil rig. Reduction is gain of electrons. So if you have an oxidation, oxidation is when an electron is lost by an element, but that has to be gained by something, and so another element must be reduced by gaining that electron that it lost. So the first thing you need to be able to do is identify whether a substance is being oxidized or a substance is being reduced. So we're going to look at a reaction and figure out how to balance it, and also which element is being oxidized and which element is being reduced. So our first example is going to be iodide ions reacting with chlorine, the element chlorine, to produce iodine, elemental iodine, and chloride ions. Now we're going to do two things here. We're first going to identify which element's being oxidized and which one's being reduced, and then we're going to balance this by balancing the half reactions and then adding the half reactions together. Now I know that you could balance this without doing that because this one's pretty easy, but we're going to do it with the half reaction method. So first, let's identify which element's being oxidized. So oxidation is lost. So let's look at the iodine and see if it's being iodide and see if it's being oxidized. It has a negative charge here. In the product side, what charge does an element have? Well, remember, elements are always neutral. So this has zero charge. So it went from a negative ion to zero charge. That means that the iodide must have lost electrons because electrons are negative. So if you throw a negative off of this iodide, it's going to become neutral. So the iodide ion is being oxidized. What's being reduced? Well, let's look at the chlorine. The chlorine has zero charge initially, and then it becomes negatively charged. So this neutral substance must have gained electrons in order to become negatively charged. So the chlorine is being reduced. The term reduced has to do with charge. The charge is going down, it's being reduced, and so that's where we get the name reduction, is lowering the charge. Okay, so we're going to balance this equation by balancing half reactions. And the half reaction simply shows the oxidation reaction and the reduction reaction separately. So iodine, we said, is being oxidized. And so this is the initial step in showing the iodide half reaction. Now to balance half reactions, well, let's write down the reduction half reaction too. So chlorine is becoming chloride. So in order to balance half reactions and balance an overall redox reaction, we need to do four things. The first step is we need to balance the atoms, or balance for mass. If you look, iodine is not balanced here and chlorine is not balanced here. So the first thing we need to do is balance each reaction to make the number of atoms the same on the left and right, which means I need two iodines on the left to balance the two iodines on the right. And I have two chlorines on the left, so I need to put two in front here to balance the chlorides on the right. So now we've balanced the atoms. The second step we want to do is balance for charge. And the way we can balance charge is remembering that electrons are lost or gained. So we're going to be either adding electrons to the reactants, or we're going to add electrons to the products in order to balance charge. So on this first one, we have two negative charges on the left. So we've got to have two negative charges on the right, and to do that, we're going to add two electrons on the right. And now two negative balances with two negative. Remember, we said that redox reactions are all about losing or gaining electrons. So this first one lost electrons. Electrons were produced in this reaction. Where did those electrons go? Well, they must have gone to this other half reaction. So if you'll notice, we have two negatives on the right. We've got to balance that with two negatives on the left. And again, we balance charge by adding electrons. So now electrons balance the charge in this reaction. So now the charge is balanced in both half reactions, and the charge is balanced in both half reactions. So our third step is we need to make the number of electrons the same in both half reactions. So we're going to balance the electrons in both half reactions. Now this example has them already balanced. There's 2 electrons in this half reaction, the oxidation half reaction, and there's 2 electrons in the reduction half reaction. So they're already balanced. 2 electrons produced, 2 electrons absorbed. It's balanced. So we don't actually have to do this step because it's already done. So our last step is we're going to add the 2 half reactions together. And cancel anything that's in the reactants and the products. So cancel anything that's the same in the reaction. So we're going to add these 2 half reactions together, which means we're going to add everything in the reactants together. 2 iodides, 2 electrons, and 2, just chlorine. So that's everything on the reactant side of the 2 half reactions. And now we're going to add everything on the product side. So iodine, 2 electrons, and 2 chlorides. So we added the 2 half reactions together by adding everything on the left together and adding everything on the right together. Now we're going to cancel anything that's the same on the left and right. The electrons always have to cancel. If they don't cancel, you did something wrong. There's nothing else that's identical on the left and right. These iodines are charged, these iodines are neutral. These chlorines are neutral, these chlorides are charged. Nothing else cancels. So now we just write our overall reaction. 2 iodides plus chlorine produces iodine plus 2 chlorides. And that is our balanced redox reaction. Now again, you probably could have balanced that just by balancing it up here, but they do get more complicated, and so this strategy works always. We're always going to follow these steps in balancing redox reactions. So let's try a more complicated one, a reaction in acid solution. Because not all redox reactions can just occur by putting things together. Sometimes they require an acid or base solution to occur. So the reaction we're going to balance is H2S, hydrosulfuric acid, and NO3, which oxidizes the sulfur and produces nitrogen monoxide. So let's just real quick look how I knew that was oxidized. Over here on the left-hand side, hydrogen's always 1 positive, and there's 2 of them. So sulfur must have been 2 negative on this side, and it went to 0. So it went from a negative charge to 0, meaning it was oxidized. It lost electrons to become neutral. So if it lost electrons, then something else must have gained them. On this side, nitrogen has an oxidation number of 5 positive. Oxygen's 2 negative, 6 negative total. 6 negative plus 5 positive adds up to this negative charge. So nitrogen was 5 positive here. Over on the other side, it's 2 positive. So it went from 5 positive and reduced its charge to 2 positive. So it was reduced. Okay, so let's write down our 2 half reactions because we need to balance this overall reaction. Now the reaction is in acid solution. We'll talk about that in more detail in just a minute, but this is going to occur in acid solution. So first we have sulfur and sulfur, so that's going to be our first half reaction. Sulfur producing sulfur. We had a change in oxidation number from sulfur here to sulfur here. Our other half reaction, nitrogen changed its oxidation number, so we went from nitrate ions to nitrogen monoxide. So these are our 2 half reactions. Now we need to balance. So remember, the first step for each half reaction is we need to balance atoms. So in this half reaction, we have 8 atoms of sulfur on the right, but only 1 atom of sulfur on the left. So we need an 8 in front to balance the sulfurs. On the next thing we need to balance in this is hydrogen. Now notice there's no hydrogen on the right-hand side, but we have 16 hydrogens on the left-hand side. Where did they go? The answer is acid solution. In an acid solution, there are two substances available to help you balance a reaction. We have hydrogen ions to help you balance the reaction, and we have water molecules to help you balance the reaction. Since we have hydrogens on the left, we also need hydrogens on the right. And where are those hydrogens? The acid solution. So 16 hydrogens on the left are going to balance with 16 hydrogen ions on the right. Because we're in acid solution, we have those available. So 16 hydrogens, 16 hydrogens. And this is a plus sign. So now the hydrogens are balanced and the sulfurs are balanced. So we first balance the atoms. The next step is to balance the charge. Notice that on the left we have no charge, but on the right we have 16 positive charges. So to balance charge, we can add electrons. So because we have positive on the right, on the right, we need to add 16 electrons on the right, because 16 negatives and 16 positives adds up to 0 on the right-hand side, and there is 0 charge on the left-hand side. So now the charge is balanced. So now we need to do the exact same thing with our other half reaction. So notice the nitrogens are balanced, so we don't need to balance the nitrogens. But the oxygens are not balanced. We have 3 oxygens on the left and only 1 oxygen on the right. So how are we going to balance oxygens? Again, acid solution. We can add waters to balance oxygens. So on the right-hand side, if I add waters, 2 of them, 2 oxygens balance with and 1 oxygen here, 2 oxygens plus 1 oxygen, gives us 3 total oxygens to balance the 3 oxygens on the left. So now oxygen is balanced. But now we've introduced some hydrogen with that water, so we need to balance the hydrogens. And how are we going to do that? Again, acid solution. We can put H positives anywhere we want to balance those hydrogens. So we need 4 hydrogens on the right, so we need 4 hydrogens on the left. And so now the hydrogens are balanced, the nitrogens are balanced, the oxygens are balanced. We've balanced everything for atoms in this one. Now we need to balance for charge. Notice on the right side there is no charge, but on the left side we have 4 positives and 1 negative. Well, what's 4 positive and 1 negative? 3 positive. So we need the left side to get down to 0. So to do that, we can add electrons. We're going to add 3 electrons because 3 negatives plus 4 positives plus 1 negative adds up to 0. So now this half reaction is balanced for atoms and it's balanced for charge. So both of our reactions are now balanced for atoms and charge. Notice one reaction is producing electrons and one's taking them in. One's producing electrons, it's losing electrons, so that's our oxidation. And one's gaining electrons, and that's reduction. So now we need to balance the 2 half reactions for the total number of electrons. If this is producing 16 electrons, they've got to go somewhere. They've got to go to this one. But this one only needs 3 electrons. So we need to find some common multiple of 16 and 3 in order to balance the electrons being produced and the electrons being absorbed. So we're going to multiply this entire half reaction and this entire half reaction by some number to give us a common multiple. So what's a common multiple of 3 and 16? 48. 3 times 16 is 48. 16 times 3 is 48. So by getting 3 of these half reactions, we produce the same number of electrons that this reaction needs to gain if we have 16 of this half reaction. So now we have the same number of electrons being produced and the same number of electrons being absorbed. So now we're ready for the last step, adding the 2 half reactions together. So we are going to add everything on the left and put it on the left side of our balanced equation, and everything on the right and put it on the right side of our balanced equation. The 3 distributes to everything inside here. So 3 times 8 is 24 H2S molecules. We also have a whole bunch of stuff here that we need to add in. So 16 times 3 is 48 electrons. 16 times 4 is 64 hydrogen ions. Big numbers on this one. And 16 times 1 is 16 nitrate ions. So now we've added everything on the left-hand side, the reactant side. we need to do the same thing with the product side. 3 times 1 is 3, so 3 sulfur molecules. 3 times 16 is 48, so 48 hydrogen ions. And 3 times 16 is 48 electrons. Then, from this half reaction products, 16 times 1 is 16 nitrogen monoxide molecules, and 16 times 2 is 32 water molecules. Whew! Okay, so we've added everything. Now we've got to start canceling anything on the left and right that's the same. We have 48 electrons on the left. They have to be canceled out with the 48 electrons on the right. Electrons always have to cancel. Is anything else the same? Do you see anything else on the left and the right? I see hydrogens here, hydrogen ions here, and hydrogen ions here. So we are going to cancel out what we can. If we subtract 48 hydrogen ions here, those go away. And if we subtract 48 ions here, that gives us a total of 16 hydrogen ions. So I think that's everything that can cancel. Looks like it. So now we just write our final equation. 24H2S plus 16 hydrogen ions plus 16 nitrate ions produces 3 sulfur molecules, 16 nitrogen monoxide molecules, and 32 water molecules. That should be our final answer. Now you just want to check, do you have the same number of atoms on the left and right, and do you have the same charge on the left and right? So on the left, we have 24 times 2, 48 hydrogens here, plus 16 hydrogens here, so 48 plus 16 is 64. And over on the other side, 32 times 2, 64 hydrogens. That checks. 24 sulfurs, 3 times 8, 24 sulfurs. 16 nitrogens, 16 nitrogens, and 48 oxygens, and 16 plus 32, 48 oxygens. So all the elements balance. Does the charge balance? 16 positive plus 16 negative? Yep, that's 0, and there's no charge over here. So this is our final balanced redox equation by using the method of balancing the half reactions and adding them together. There are plenty of examples of these online. You're welcome to check those out if you need some more help. You're also welcome to talk to me if you need some more help. Remember, the key thing though is the 4 steps that I talked about. Balance your atoms on each half reaction, balance your charge by adding electrons, balance the electrons in both half reactions, and then add your half reactions together and cancel what you can. If you need any help, let me know. Good luck.